and welcome back to Diligent Automation. In this episode of our Sugar Refinery automation series, we are going to continue with the engineering of the automation system. In the previous episode, we discussed the overall system architecture and some of the major considerations behind our hardware selection. Now we will take those engineering decisions one step further and start building the actual hardware configuration and bill of materials using Rockwell Automation's Integrated Architecture Builder, or IAB. As we go through the configuration, I will explain not only what hardware we are selecting, but also why we are selecting it. Because in a real industrial automation project, preparing a BOM is not simply a matter of selecting part numbers from a catalog. It starts with understanding the application and developing the right architecture. Before we start selecting hardware in IAB, let us briefly understand the application. This is a large sugar refinery automation system with approximately 2,500 field I/O points. The equipment is distributed across different areas of the refinery, including the 8-meter level, 16-meter level, dome area, and boiler area. We also have multiple intelligent IMCC panels containing a large number of motor starters, soft starters, and variable frequency drives. So this is not simply a PLC with a few local I/O modules. We are designing a distributed automation system consisting of multiple controllers, remote I/O stations, intelligent motor control systems, SCADA communication, and an industrial Ethernet backbone. That physical and functional distribution has a major influence on our architecture. Now let us start with the controller platform. For this project, we have selected the ControlLogix 5580 platform with the 1756-L83E controller. The L8 series gives us significantly improved processing capability compared with the previous L7 series generation. It also provides an embedded gigabit Ethernet interface and sufficient user memory for our application. However, controller selection should never be based only on memory capacity. We also need to consider program complexity, scan time requirements, communication loading, the number of connected devices, future expansion, and most importantly, the nature of the application. For this project, the L83E provides a good balance between performance, memory, communication capability, and future scalability. Another important decision is that we are not trying to control the complete refinery with one large processor. The refinery is naturally divided into different process areas. Therefore, where required, the control application can also be logically distributed across multiple processors. This provides several advantages. The processing load is distributed. The PLC programs can be organized according to process areas. Troubleshooting becomes easier, future expansion becomes more manageable, and a problem associated with one controller does not necessarily have to affect every other process area in the same way. This is particularly useful in a large continuous process application. At this point, I would like to emphasize one very important engineering principle. The philosophy I am describing here applies mainly to large process automation applications such as sugar refineries, cement plants, steel plants, power plants, chemical plants, and similar continuous process industries. I would not automatically follow the same approach for machine automation or OEM machine programming. In a machine application, sequencing, motion control, servo synchronization, local I/O, drives, and other functions may be very tightly coupled. In that situation, a single high high-performance controller is often the cleaner architecture. If additional memory is required, selecting a higher capacity controller, such as an L84E or L85E, may be more appropriate than unnecessarily dividing one integrated machine application across multiple processors. So the important point is this: the best controller architecture depends on the nature of the application, not simply on controller memory capacity. Now, coming back to our sugar refinery project, let us look at the communication architecture. In a large automation system, I prefer to organize communication according to its function. The upstream network handles communication toward the SCADA and plant level systems. The downstream network handles communication with the distributed controllers, remote I/O systems, and other automation equipment. Separating these functions gives us a cleaner architecture and makes the network easier to understand, maintain, and troubleshoot. But because our refinery equipment is physically distributed across several areas, we also need a reliable backbone to interconnect these locations. And this brings us to an important part of this project: the fiber optic network. The refinery control system is distributed across the 8-meter level, 16-meter level, dome area, and boiler area. The overall network extends across approximately 500 meters, although the individual point-to-point connections between the network switches are maintained below approximately 150 meters. For this communication backbone, we selected managed Ethernet switches interconnected using 1 gigabit per second multimode fiber optic links. There are several reasons for using fiber in this application. First, it gives us a high-speed communication backbone between the different refinery areas. Second, fiber provides excellent immunity to electromagnetic interference. This is particularly valuable in an industrial environment containing large motors, variable frequency drives, MCC panels, and high-power electrical equipment. Fiber also provides electrical isolation between the interconnected areas. So this is not simply a decision based on distance, it is also about creating a robust industrial communication infrastructure. The 4 managed switches are interconnected to form a device-level ring, or DLR network. This ring becomes the backbone of our downstream automation network. The controllers and remote I/O systems in the different refinery areas connect into this network through the respective managed switches. One of the major advantages of a ring architecture is network resilience. Under normal conditions, communication operates through the ring according to the DLR mechanism. If a single network link is interrupted, the DLR architecture can provide an alternate communication path around the ring. This helps maintain communication between the connected automation devices and improves overall system availability. For a continuous process plant where communication reliability is extremely important, this is a significant advantage. So our choice of gigabit multimode fiber together with the DLR topology is an engineering decision based on plant layout, communication performance, industrial noise immunity, maintainability, and availability requirements. Now let us move to the remote I/O architecture. With approximately 2,500 field I/O points distributed throughout the refinery, bringing every signal back to one central control panel would not be practical. It would significantly increase field cabling, installation effort, panel requirements, and troubleshooting complexity. Instead, we distribute the remote I/O panels closer to the field equipment. The field signals terminate locally at these remote I/O stations, and communication back to the controllers takes place through our industrial Ethernet network. This reduces long-distance field wiring and gives us a much more structured architecture. For this project, we are using the PointMax I/O platform for the distributed remote I/O stations. Here, I am configuring the required digital and analog I/O modules according to the estimated requirements for each process area. While selecting these modules, we should not simply match the current I/O count exactly. We also need to maintain reasonable spare capacity. During detailed engineering and commissioning, additional instruments, interlocks, or field signals may be identified. If every channel is already occupied, even a small modification can create unnecessary hardware changes. At the same time, excessive spare capacity increases project cost. So the objective is to provide reasonable engineering margin without unnecessarily oversizing the system. The remote I/O stations do not necessarily have to be identical. One process area may contain a large number of digital devices, another area may contain more instrumentation and therefore require more analog inputs. The module configuration should therefore follow the actual I/O distribution of each process area. This also makes commissioning and maintenance easier. When an engineer identifies a field problem, the process area can be quickly associated with the corresponding remote I/O panel, network connection, and controller program. Another important part of this project is the intelligent MCC system. The existing IMCC panel hardware will be retained. However, the PLC programming, communication integration, and control logic associated with those panels are included within our project scope. These MCCs contain a large number of motor control devices, including DOL starters, soft starters, and variable frequency drives, so their communication and integration must also be considered as part of the complete automation architecture. Again, the important point is that we are not designing the PLC, I/O, MCC communication, and network as separate systems. They are all parts of one integrated automation solution. Now, as we continue building the architecture inside Integrated Architecture Builder, we can gradually see how our engineering decisions are converted into an actual hardware configuration. The controller platform, communication modules, remote I/O stations, and associated components are brought together into one system. At each stage, I recommend verifying the configuration rather than waiting until the very end. Check the controller, check the communication modules, check the remote I/O adapters and I/O modules, check the quantities, check the available spare capacity, and compare everything against the project I/O list, motor list, and architecture documents. Finding an error here is much easier than finding it during panel manufacturing or site commissioning. Once the architecture has been configured, Integrated Architecture Builder can help us prepare the hardware bill of materials. This is one of the major benefits of developing the architecture properly inside IAB. Instead of manually creating a list of part numbers, we are generating the BOM from an engineered system configuration. But remember, software is an engineering tool. It does not replace engineering judgment. Before releasing the final BOM, the engineer should still verify the part numbers, quantities, compatibility, spare capacity, communication requirements, and project-specific requirements. The final responsibility remains with the engineer. So, in this episode, we have moved from the basic engineering concept toward an actual automation hardware architecture. We looked at the ControlLogix controller platform, distributed remote I/O architecture, communication requirements, and the gigabit multimode fiber DLR backbone connecting the different refinery areas. And finally, we used these engineering decisions to build the system configuration and prepare the bill of materials. The important takeaway is that a good BOM is not simply a collection of catalog numbers, it is the result of good system engineering. And with that, we have come to the end of this episode. I hope this session has given you some useful practical insights into real-world automation engineering and the engineering thought process behind our decisions. We will meet again with more real engineering work from different industrial automation projects. We will explore different applications, different challenges, different control architectures, and different engineering solutions. Wherever possible, I will try to take you beyond textbook concepts and software demonstrations and show you how engineering is actually approached in real projects, from understanding the requirement and developing the architecture to PLC programming, SCADA development, networking, commissioning, troubleshooting, and optimization. Every project gives us something new to learn, and I look forward to sharing those engineering experiences with you through this channel. Thank you very much for spending your valuable time with me and for supporting Diligent Automation. If you find these videos useful, please share them with fellow automation engineers and subscribe to the channel so that we can continue this practical engineering journey together. Thank you once again for watching. We will meet again in the next episode with another real engineering challenge and another opportunity to learn together.